Now we're going to move on to the topic of initialization. Because Fluent uses an iterative method to solve the governing equations, all solution variables need to be assigned an initial value, or initialized, before iterations can begin. Although the final solution is independent of the initial guess, a realistic initial guess improves solution stability and accelerates convergence, and in some cases a poor initial guess can cause the solver to fail during the first few iterations. 5 initialization methods are available in Fluent, and these include standard initialization, patch values, hybrid initialization, FMG initialization, and starting from a previous solution. In the next slides, we're going to go over each of these topics and give more information about each one. The first 2 items listed on the previous slide were standard initialization and patch values. For standard initialization, you select Solution Initialization here, and then choose the button for Standard Initialization. Normally what happens is an inlet boundary is selected in the drop-down list under Compute From, and then Fluent automatically fills in the values for each of the variables in the panel here using whatever values were entered in the Boundary Conditions panel. Standard initialization fills every cell in the domain with the same value, but sometimes it can be beneficial to have different values of the same variable in different regions of the domain. This is what patch values does. You open the patch panel by selecting Patch in the Solution Initialization page. Instances where patching can be advantageous include free jet flows, where you can patch a higher velocity in the region where the jet is, combustion problems, where you can patch a high temperature region to initialize reactions, and multi-phase flows, where you may patch different phase volume fractions in one or more regions. You can also use cell registers, which are created by marking cells in the adaption panel to patch values into different regions of the domain. The default initialization method is hybrid initialization. It works by providing a quick approximation of the flow field using a collection of methods. To determine the velocity and pressure fields, Laplace's equation is solved, and all other variables, temperature, turbulence, species, volume fractions, are automatically patched based on domain average values or on some particular interpolation method. The graphic on the right shows how to access settings that are associated with hybrid initialization, but it's normally not necessary to modify any of these settings. The fourth option for initializing the solution is full multigrid initialization, which is also commonly referred to as FMG initialization. FMG initialization can be used to create a more realistic initial flow field than the other methods, and so it's especially useful for complex flow problems that involve large pressure and velocity gradients on large meshes. The way it works is by using the full approximation storage, or FAS, multigrid method to solve the flow problem on a sequence of coarser meshes. And what it does is on each of these coarse meshes, it solves the Euler equations with first-order accuracy. FMG initialization is only available as a text command, which is solve, initialize, FMG initialization, as you see here. And then there's also another text interface command, solve, init, set FMG initialization, which can be used to access certain settings that are associated with the FMG initialization. The final method of solution initialization is starting from a previous solution. The solution interpolation function allows a previously calculated solution to be used as an initial condition if you've made some changes to the case setup. What you have to do is write out a solution interpolation file from File Interpolate from the original case, and then when you read in the new case, you go back to the interpolation file and read the file back in. This is especially useful for starting fine mesh cases when there's a coarse mesh solution is available. And once the interpolation file has been read in, if you start to iterate, it will always use the interpolated solution as the starting point. Another way of starting from a previous solution is to first solve a simplified version of the real problem in order to provide a good initial guess. Some examples are listed here in the table, where if you're solving for heat transfer, you might start by solving an isothermal flow. If you have a natural convection problem, you might start with a lower Rayleigh number by reducing the strength of gravity. For combustion or reacting flow problems, you might start by solving for cold flow. And for turbulent flows, you might start with an inviscid Euler solution.